Last time we saw the different types of reactions. We saw combination, decomposition, single and double replacement reactions. Now I want to show you this type of reaction, which is called oxidation reduction reactions, or redox for short. Even though it's a pair of reactions, we look at them at the same time because when one is happening, the other one has to happen at the same time. When we look at oxidation, we're looking at a reaction that involves an atom losing electrons or an ion losing electrons. And when we look at a reduction, it is an atom or an ion gaining electrons instead. And that's why they are both treated as one reaction, because for one to lose electrons, the other one must gain electrons. You can think of this so it's sort of like any transaction. Let's say you go to the store. When you're losing money, the cashier is gaining money. So both things happen at the same time, even though they're two separate events. So oxidation is the loss of electrons, and reduction is the gain of electrons. I was taught by a student a few years ago this little acronym that actually helps remember redox reactions. It's an acronym called OIL-RIG, and this stands for oxidation is losing, reduction is gaining. So that's, I don't know, just a suggestion here for how to memorize these definitions. The one thing that they both have in common is that we have transfer of electrons. They're moving from one place to another. Here we have a typical redox type reaction. We have solid zinc interacting with copper in solution, and the zinc will migrate to the solution and the copper will take the solid form. As you can see, zinc turns into zinc plus 2, so that means that it lost 2 electrons. Remember that we either gain or lose electrons. We cannot gain or lose protons. If we lose or gain them, we're changing the identity of the element. On the other hand of this equation, we have copper plus 2. That means that it's missing 2 electrons, turned into copper, so it gained 2 electrons. So when copper plus 2 turns to copper, we say that copper is being reduced. When zinc is turned into zinc plus 2, we say that zinc is being oxidized. And that's pretty much how you will go about classifying what part of the reaction is oxidation, what part of the reaction is the reduction. Just keep an eye on those charges. This is the format that we will be seeing, especially for the quizzes and tests. You will start off with 2 different compounds. Copper plus 2 can also be in the form of a salt. So for instance, I can have, let's say, copper sulfate. And this is an ionic compound. And inside here, we know that the sulfate has a -2 charge, so the copper has a +2 charge. So that means that copper plus 2 can be either in this form or as a compound without explicitly showing you the charges. So again, we look at zinc. It starts by itself as a solid compound, then it turns into an ion, so it lost 2 electrons, so it got oxidized. Copper was in the form of a salt, now it's in solid form, 0 charge, so it gained 2 electrons. Therefore, it's a reduction. Now, one other definition that I'd like to go over is what we call the reducing and oxidizing agents. A compound, let's say if you look at zinc turned into zinc plus 2, so it got oxidized. By getting oxidized, it's forcing copper to get reduced. Because it's forcing copper to be reduced, we call zinc the reducing agent. The opposite is also true. Copper is being reduced, therefore it's forcing zinc to be oxidized. Therefore, copper plus 2 is also known as my oxidizing agent. What we have right here. So the agents, whether it's oxidizing or reducing, is going to be based on what that ion is doing to the other species in the reaction. We have a few scenarios here, and the way that we predict these charges is pretty much the same one that we use to predict charges in ionic compounds. If the electrons are on the product side, as we see here, that means that the electrons are being lost. So I had sodium, now I have sodium cation plus an electron that went somewhere. So this is the way that I represent my oxidation reactions. And then because reductions are the opposite, then I would have my elements or my ions plus whatever many electrons I'm adding, I'm gaining. Then I have my product. So that would be a reduction reaction. When you combine the oxidation and the reduction for a given reaction, it should give you the net reaction of the actual chemical reaction. That means that the same number of electrons that are on the reactant side should appear on the product side as well. Kind of a charge balance thing that we're doing here. A few examples. Iron rusting, I think that's the most classical, most obvious example. Iron by itself has this formula, just Fe, but in the presence of oxygen, whether it's in the form of water or just being exposed to the air, it turns into iron oxide. Now this iron, remember that this is an ionic compound, metal, non-metal, so there must be a cation and an anion. Oxygen has a -2 charge, 3 oxygens, that would be -6. So these two irons must have a +6 to cancel out that -6. That leaves with each of the iron atoms or ions with a +3 charge. In batteries, your typical batteries work through redox reactions to generate electron movement, which will generate the charges that we use for flashlights in this case. And I brought this up because I think it's a really good example related to healthcare or pacemakers. They're made of something called lithium-ion batteries. These are really, really long-lived batteries. They have like 5 years life. And again, they work through a redox type reaction. And that's it for redox reactions.